Testing? Well, let's see here. Testing. That might help. It is about Data Studio some, but it's really more about query performance and optimization and how to read the explain and what goes on with our queries and what we can do to help fix some queries to get things to run better. There's a lot of query tools on the market. There's a lot of explain tools on the market for years on the mainframe side and some of the GUI tools. Me personally, you know, I do a lot of performance and tuning at different companies and have over the years. I grew up as a developer and got really good at SQL and got really good at performance and tuning. And when this tool came out, when the Visual Explain came out in version 8, and then they eventually got it into this Data Studio, I know it's a bit cumbersome, and companies have a little bit of a problem rolling out and all the changes and a lot of the issues they had in the earlier versions of this. But me personally, I love the tool. A lot of times I'll use a mainframe, some mainframe tool, whatever suite of tools that a site has, to do an explain, and you can get some great information out of the plan table. But it never, sometimes it doesn't go deep enough. So to try to understand exactly what's going on or why the optimizer chose an index or why it chose a join order or why it chose a table scan or why, that's where this tool I really like. So if I'm on some projects or if I'm helping with some projects, I want developers to have this tool. I want every developer to have it for a couple of reasons. Get them to do some explains and look for some of the obvious things, but it gets them to know their data really quick too, because you can just do a select asterisk from table and do an explain, and it comes up, and of course you're going to see a table scan. But you can click on the table, and we're going to see, and you can see everything about that table. You can see the columns, you can see the indexes, you can see the partitioning, you can see any special statistics. You can see everything about that table. Because the most frustrating part with working with a lot of developers, sometimes they don't know their data well enough. And this is a great way that they can just click, 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 click. And this is what I do when I go into some sites. I'm not familiar with their data all that much. And I'll do that, and I can spend 10, 15 minutes, and I can just start going down, seeing all the statistics, the cardinalities, and I get to know the data pretty well in a matter of like, 10, 15, 20 minutes. So we're going to go into some query tuning. We're going to show the visual graph and some other things with Data Studio here. So we're going to get a little bit. We're going to get a little bit into optimization. Something called filter factors. It drives everything. Drives all the optimization choices. It drives what index is going to be chosen. It drives the order of the tables. It drives like all of optimization. So we kind of have to get a good handle on what that is, and this tool shows it to us like pretty easily. We can get those things from mainframe and other kind of query tools, but you have to dig a little bit deeper. Or a lot of times on the mainframe, whatever suite of tools you have, you can get an explain, but it doesn't show some of the other tables of information where things like this are, which is down in what we call the DSN predicate table. Okay, a lot of times they just bring up the plan table, and we can see some of the obvious things from the plan table, but it doesn't show a lot of the other. There's like 28 tables or something, that you have to create to use this tool. Okay, so let's just talk about improving SQL performance. I mean, if you have some things that aren't running very well, a query or a program, maybe an application, you kind of start breaking it down. And with developers, I'm always trying to get some more and more developers empowered. There's a lot that we can do to get things to run faster without talking with anybody. Okay. And one of the first things that we can do as developers is change the SQL, okay? But you have to be a little bit stronger in the SQL language. Sometimes there's 4, 5, 6 different ways to write a query to get the same results. Sometimes you can write a predicate, one of the statements in your where logic, a different way that'll sometimes change the optimizer to go down a different physical path in bringing back our result set. So one of the first things I tell developers, like, look, if you don't have the explain tool, if you don't do an explains, if you have something that's not running very well, and you're not quite sure what to do, the first thing you should start thinking about is, can I change the SQL in any way? Can I rewrite it in any way? And sometimes developers will go to rewrite like a predicate, and they'll go, well, that just seems kind of silly. Well, sometimes you can change it, nothing will happen. Sometimes you can change it, it could get worse. The key is we're trying to get the optimizer to do something different. If I want to get the query to run differently, I have to get the optimizer to do something different. This is a big part of what we are empowered to do without getting anybody involved. So when I get into some performance and tuning assignments, probably 85% of the time, all I do is change people's code. I restructure their queries and I redesign their programs. Okay, that's big. Yeah, the other 15% of the time, I'll get with DBAs and we'll tweak some indexes, we'll tweak some statistics. But most of the time, all I do is change code. So the developers are empowered to make things better, okay? They just need to be more educated. They need to get stronger in SQL. They have to understand optimization a little bit more. That's why I know when I'm on projects, I want every single developer to have this particular tool, because I just happen to really like it, because they can do quick explains and they can see all kinds of information on the tables, okay? So there are some things at a system level we don't get into in this presentation. There's a lot of Z-parms, you know, that can have some effect on performance. But it's these three things down here: changing the SQL. Statistics are big. Statistics are usually kept up to date pretty well in the production side. In the test environment, statistics are not so much kept up on a weekly or daily or current basis. So we have to pay attention to that. If we're running some things in a test environment and we're having some issues, we need to pay attention to the statistics. How current are they? And is the environment that I'm working in, is it anywhere close to a production environment? You know, every company, to me, should have a test environment that mimics production. So we don't have those Sunday night, you know, last minute, we're moving things into production and we're seeing things different on the explains. What we see different could be good. What we see different could be bad, but we want to minimize those surprises. So that's always a big problem still. We don't need to have all the data. If we got a billion row table, we don't have to have all billion rows in a test environment, but we want to make sure we have the statistics in our test environment. It says there's a billion rows in this particular table and some of the cardinalities. So we're going to look at some of the statistics. In the physical design, you know, partitioning, of course, you know, get the right partitioning depending on how our application goes after the data. The only comment I really have about changing the physical design is when new tables are created, we as developers need to pay attention on how the data is physically clustered, okay? So some of the examples that we have coming up here are based on these set of sample tables in DB2. The employee table, okay, the employee number, last name, first name, middle initial, all that, is in these examples, is in employee number order. So on page 1, 4K page of the physical file, page 1, offset 1 is employee number 10. Page 1, offset 2 is employee number 11. Page 1, offset 3 is employee number 20, so on and so forth. It's in employee number order. But what if my application, we do a lot of grouping by department number? What if I see like 90% of the joins to that table is where a department number in some other table is joining to a department number in this table? What if we're going after in our batch queries that are getting the most data, we're going after some kind of other ranges or of information that's not a range of primary keys? So what I see a lot of times is on the physical design, I see a lot of times where the tables go into production in a primary key clustering order. That's not the way we go after the data, except by a specific primary key where we get one row back in a lot of our online transaction processing. So it's something that we can't rely on the DBAs to make sure they get it correct. We as developers have to make sure we communicate with the DBAs, say, look, this is how we go after the data. If I see a lot of that stuff by department number, that table should be in department number clustering order. On page 1, we should have A00 and all the people that are part of A00, followed by the next B01 department, followed by the next C01 department, and that's the way it should be physically clustered. So the problem is once these tables are in production, I can go in, or somebody can go in and say, you know what, that table should probably be in another physical order. Well, it's almost an impossibility to change it at that point. It's in production. There's a lot of queries running against it. It becomes a huge project because we can't just, it is an easy change from a DBA perspective, but it could really affect a lot of queries in a good way. It could affect a lot of queries in a bad way. So the whole application needs to be retested. So it's kind of tough once it goes in there. So developers, and this is kind of where I come from, is educating developers and getting them stronger at things and getting them more empowered. They need to focus on a number of things. What are the indexes on a table? And how do the indexes work? I mean, there's a lot of times developers that go, yeah, I know that index help us out, but they don't really know how they work. Predicate types. When we talk about predicates, we're talking about statements in a where clause. Where last name equals Andrews, that's a predicate. And first name equals Tony, that's another predicate. And department number is in, and so on and so forth. There's different predicate types. There's range predicates, betweens and greater than, there's equal predicates, there's subquery predicates, there's all kinds of different predicate types. Access path choices, there's a lot of different choices that an optimizer can make. So, when we send a query that says where last name equals Andrews and employee number is between and department number is in, if I have an index on employee number and an index on department number and an index on last name and all those indexes, the optimizer, when it receives a query, or it's during bind time, or if it's dynamic, it receives a query, it looks at the from, says what tables is your query going after? And the optimizer code goes and starts querying the sysIBM.sys tables, okay? Sys columns, sys indexes, finds out everything about what we're going after. It looks at our where clause. Is there anything in our where clause that matches any of the indexes? And then it starts making cost. Say, okay, well, you have 3 predicates here, and I have 3 indexes, and I got each of those predicates match an index. Which one do I use? Okay? And it starts going through the costing of that. It could use the first index, the second index, the third index. It could use a combination of the first and second, first and third, second and third, first, second and third, and maybe not use any indexes at all. And it goes through all these choices and comes up with what it thinks is the best index to use, or the best thing, maybe a table scan. So the index that it's going to choose is all based back on these filter factors. Okay? It looks at our where logic and says, if I go use this index, how many last name Andrews is there going to be? If I use this employee number index, how many employee numbers between my range am I going to get? And it goes through each of those, and it's going to pick the one that it thinks is going to get the least amount of data, because that's then going to probe that index, use those indexes to go find the data, and then bring it to our result set. It's not correct all the time. Okay, it's correct most of the time, but that's the way it is costing things out. So we're going to look at some statistics, especially what we call data outliers. When we get into some data, like we have, I think maybe an example here. There's a column called commission, okay? And in the commission column, there's 31 different values across our data. Okay, 31 different commissions that are paid out. But 90-some% of them are 0. Okay, that's an outlier. If we use commission in any kind of where logic, we need to get with the DBA and have some special statistics on that outlier, so that DB2 knows that the value 0 is 90-some% of the data. Okay, now why is that important? Because if I use it in some where logic, then the optimizer can help choose what it thinks is going to be the final result set, the number of rows, maybe the join order, because that could be some more filtering on a certain join. And if it thinks it's going to join a lot or join not much, it may not use that table as the starting table. It can have a lot of effect in optimization. But when we run the statistics, we as developers have to do something different. We can have all the greatest statistics, but if I come in with a query that says where commission equals host variable, the optimizer is going to go, okay, you're going after some value. I don't know what the value is. Okay, I'm going to go look in the statistics. There's 31 different values. I'm going to assume that predicate is going to hit 1/31th of the data. It's going to assume that all the values are evenly distributed. It doesn't have anything else to go on. It's the most common filter factor, because we use host variables often. And we want to use host variables. But in these cases with these outliers, we have to get some special statistics, and we have to change our code. So in our code then, when I come in our code, I'm going to say, okay, when I go into a query, if my commission in the host variable equals 0, I'm going to execute a query that has all my where logic and commission equals 0, and you hard code it. Because when the optimizer goes down and it sees a hard-coded value, it's going to go look in the statistics, in the sys column distribution, and say, what do I know about that value? Or what do I know about any other values? If I don't give it a hard-coded value, it doesn't go and look there. Okay? So when it goes and looks there and says, oh, value is 0, that's like 90-some% of the data. So that predicate is really not filtering hardly anything. If it's not 0, then in my code, I need to say where the commission and commission equals host variable and the commission does not equal 0. It's some value. I don't know what the value is, but it doesn't equal 0. The optimizer is going to see a hard-coded value. It's going to go look up and say, what do I know about that value? Or what do I know about any values? It's going to say, oh, 0 is 90-some%. You're looking for some other value because you have not. So that's going to really reduce our result set. And that can have a big change in optimization. Join order, join type, maybe an index choice. You can have a lot of different things can happen. Clustering order of data, we talked about that. You know, developers should know what the clustering order of the data is and how it's all, you know, physically clustered. We're going to look at some table space scans. Okay, I think every developer should be doing an explain. Okay, and I get around sometimes people have been coding 10, 15, 20 years in DB2. They've never done any explains. To me, I just shake my head. I can't believe it. And a lot of times in their defense, the management doesn't want them to do explains. Just hurry up and get the data, get it right, get a sign off, and send it off to a DBA to take a look. Well, I think that's our responsibility as developers. Get the data right, number one, always, and number two, get it back as fast as we can. It's the same thing when I was developing on projects, you know, 20 years ago. Same thing today, but that getting it back as fast as you can has kind of gone away. So doing some explains, especially in any kind of tool, is really quick and easy. So we get to look at some obvious things I'm going to point out here. Table space scans obviously are one of them. And if they get a table space scan, they need to know why are they getting a table scan. There's a screen coming up on that. Stage 1, Stage 2 residual predicates we're going to talk about. Sorts that are going on. Are there any sorts going on? You'll be surprised how many queries in production have sorts going on that don't need to be sorting anything. They have distincts, they have group bys, they have order bys. They don't even need them in there. Okay, and a lot of times those things cause sorts. And then of course, you know, any kind of possible rewrites that we can do. Okay, so I talked a little bit about the optimizer. The optimizer, you know, at bind time for those packages that get built, or if it's a dynamic query and it's being bound at runtime and at prepare, and it's being you know, the information being put in the statement cache. It looks at the from. What tables are you going after? It looks up all these information on the tables. It looks at the statistics in the tables. How many rows are in the table? What are the partitions? How many rows are each in partition? It looks at the where logic. You know, and for each column in your where logic, it looks at what does it know about that column and looks up statistics there. Because if I go where employee number equals, it's going to say, well, your table has 51,000 rows and your employee number has 51,000 different values. Well, that's going to greatly reduce the result set right away. Okay? If I just say where department number equals, it's going to say, well, your table has 51,000 rows, but you only have, like, say, 8 departments. So you're going to get a bigger result set back. Okay? So it starts looking at these statistics, especially based on the columns in our where logic, and it looks at how the SQL is coded. The SQL language is great, and it's awesome, and we can do all kinds of things with it. But there's a lot of things in the SQL language, the way that we code it is not efficient in these relational database systems. It's not efficient in DB2. A lot of times the same thing is not efficient in Oracle or SQL Server, Informix or Sybase, or you name one of them. Okay? So the way that we write our SQL, we have to like really watch out, because we could take away the use of indexes and knock these, what we call these predicates, down to a stage 2 or a residual, or on the LUW it's a residual and sargeable kind of level, and we don't want those. So we can rewrite things like different way. So the logic, I mean, SQL gives us the logic to code in a lot of different ways. But a lot of the ways in the SQL language is not very efficient. We have to watch out for that. You should have standards and guidelines and drive it home to your development teams. Do not code things this way, you know. And so there's some other things that actually have an effect, you know, and this stuff can be brought over in some ZPARM, some information in a test environment. You know, the CPU could be different, you know, in a test environment than what we have in production. You know, our RID pool, our sort pool sizes could be much smaller. So we have to That doesn't have as much of an impact as regular statistics do, but it can catch us at times. So in order to do an explain on the mainframe, we typically only need a couple of tables. A plan table, of course, that's been around for like 35 years. The statement table's been around for probably like 30 years. You know, function table's been around. But there's a whole bunch of other ones that the tool actually has to have. So if you're using this or you're moving into a data server manager, you need to have all these tables created. It's about 28 of them, I think, give or take. And you can create one set, and everybody can use the same set. You don't have to create one set for like each different developer. But the tool, this tool has to have all of them. Okay. So, you know, you set this Data Studio up, and you start putting in your queries, and you start doing some explains, and you can run the explains. I mean, you can actually run the queries. You can explain the queries. This is what we're going to get into here a little bit. And you know, telling us like what this is the version 12. You know, picture here on a version 12. You have all your connections over here. Okay, so when you run an explain, obviously we get the visual graph. Okay, the visual graph is not a hard thing to read. A lot of people say like, oh yeah, it can get kind of crazy if you have a 5 or 6 table join. You know, it can get very busy. But it's telling a story of what's going on in the running of the query. In this particular query, it's telling us it's going to start at this index here. And you might go, well, what's the index? Well, if you click on that, you're going to get information over there and find out what the index is. Okay, this particular index is a composite index. It's made up of last name, first name, middle initial in our examples here. In that index, there's 47,777 entries. The index is a separate file than the data file. So if you go look that up, it's a 3-column composite index. So that's telling me there's 47,000 different last name, first name, middle initial combinations in our data. So if you go in and you say, well, last name equals Andrews and first name equals Tony and middle initial equals A, the optimizer can look up some of the statistics and go, wow, there's 47,000 different combinations out of 51,000 rows in the table. You're not getting a whole lot of data back. And it makes decisions accordingly. So we can see right away some information on data distribution. I love this for developers. You know, I mean, you ask a developer some kind of question like that. You know what the answer is? I don't know. I mean, this is a real quick and easy way for them to kind of get to know their data. So we see some numbers here. Now the numbers on the, is there any LUW people here, by the way? Yeah, the number on the mainframe, we actually get cardinality numbers out of the explain. On LUW, you get costing numbers. And there's not an option in there to say, I don't want the costing numbers, I want to see cardinality numbers. Because this is actually telling a story, saying, I'm going to probe that index, and out of that index, I think I'm going to find about 2 rows that meet the criteria. So if I back up here, there's the criteria. Last name Smith, first name Joe, and a couple other things there. Okay? And it thinks it's going to find 2 rows, and then those 2 rows, the 2 rows entries out of the index is going to take the address of where the rest of the data lives for those rows, and it's going to come over to here and grab those rows on the pages because it has a couple of other predicates it needs to check. Because in that index, we only have last name, first name, middle initial. That's all that's in this physical index file, along with the address of where the rest of the row lives. So it's got to go get the row then and then check these other predicates right here. So there's a little bit of I/O, get pages, probing of this index here. It's got to come over here to the data file, do that get page, bring it up, check the other predicates. It thinks ultimately it's going to get 1 row back. Okay, so, I mean, that's a pretty good story. Is it real? I don't know. We could go compare it against reality. We could go run the query and see what happens.
What's the 10044?
Oh yeah. So behind the scenes, a lot of the numbering they use are these decimal 31 numbers, and sometimes they actually will show some of the decimal number, and then they don't show it there, but they show it here. Yeah, okay. Yeah. It's the same one. Yeah, yeah, good. These little numbers here, by the way, in parentheses, these really have there's no disregard them. They don't mean anything. It doesn't. There's nothing logical to them at all. And IBM actually even knows that. But they have, for some reason, they haven't never taken them away. In LUW, this is what we get. You know, we get these costing numbers here. LUW gives us all kinds of like costing numbers that come out. So when you're rewriting some queries and you're looking, I mean, one of the things we may look at are like some costing numbers. If the costing numbers go down, there's a pretty good chance it's probably going to run better. Is it a guarantee? No, it's a guesstimate from the optimizer. Okay, I've seen numbers come way down and run way worse. Okay, it's a guesstimate. But if that's all we got to go on, you know, if we have statistics in a test environment, but we don't really have the billion rows physically in there, it's a good kind of guideline to go by. All right, these are all called sources of data. You can just click through these. You get all kinds of information over on the left. That's why I said if I do a select asterisk from table, I'm going to see this table, and I'm just going to click on that, and I'm going to get all kinds of information on the left-hand side as I click on each one of these nodes here. So like this, if you click on one of these nodes, here's the XEMP03, which is an index. You can get over here and you can start looking down and seeing some things on the physical side and some of the statistics based on that index. What are the columns of the index? All kinds of information over there. So the first key cardinality is something that always gets driven by run stats, and that is the first column of the composite index. What's its cardinality? And then what's the full cardinality? So this is telling us that there's 947 different last names in the data. But last name, first name, middle, initial together, the full 3 columns composite is 47,777. That's good stuff to know. You know, that's data distribution information there. Data retrieval. So when your where logic gets applied at a couple of places. There's some predicates that if DB2 chooses to use an index are going to get applied at the index. The other predicates are going to get applied after it goes and gets those rows based on the index entries. So for example, if we go back to here, this query back here, last name, first name, it's going to use those 2 predicates to probe the index and find all the Joe Smiths. And it's going to take the addresses of where the rest of those rows, where do those rows live. It's going to take those over to the data file. So there's I/O going from the index file over to the data file, get the pages that those rows are on, bring them up into memory, and it's going to check these other predicates right here. So predicates are getting applied one of 2 places, either at the index and or at the data side, and it gets split out. So when we come back to so we come back to here, trying to figure out where I was. This is going to show us the predicates applied to the index. Okay. Now, the one thing about this, it says IX scan. So one of the things that we need to make sure of with people that are getting explains wherever they're getting explains, they can't just go and say, oh, it's using an index. We have to go one step further. How is it using the index? Is it scanning the index file? Is it probing the index file? When I talk probing, we get something that's called matching columns. Last name equals Andrews. It can go down to that index very quickly and find where the last name Andrews starts and find all the entries in that index where the last name equals Andrews. The index file is in ascending order. So if you look at the way these indexes are built, it's upside down, you know, kind of tree, and it's got this root page up there. I kind of think of the probing of the index like a binary search in programming. So it comes in, and up at this root page, you know, say like, well, half the entries go this way, and the other half of the entries go this way. You know, from Adams to, you know, whatever, Miller go this way, and the other ones like go this way. Or maybe to split up into thirds at the root page. But it's kind of like a binary search. So if I have a physical index here that's in last name order, and I come in and say where last name equals Andrews, I kind of think of it as a binary search. It slices that index in half. Says, is the value I'm looking for in the top half or the bottom half? Well, Andrews is on the top half because all that file's in ascending order. So let's split the top half in half. Is Andrews on the top half or the bottom half of that? Let's split that in half. Let's split that, and that's what the probing is doing of the index file until it finds Andrews or it doesn't find all the Andrews entries. So if I have last name, first name, middle initial, and I come in and I say where, just select from the table where first name equals Tony. can it probe the index? First name equals Tony. No, because the index is in last name order first. So for first name equals Tony, can I split that index in half and say, are the first names equal Tony on the top half or the bottom half? It can't. The first name Tony could be in any last name in the index file. So in a lot of cases like that, it may choose to use the index, but as we click on this, we get information that says it's not really matching anything. So we're not really probing, it's going to scan the index. That means it's going to go to the index file, start at the first entry, Andrews or Adams, whatever it is, and it's going to check through every entry in the index looking for a first name equal Tony. That's not good response time. So a lot of times we have to pay attention that we see an index, and this says index scan, but it doesn't mean it's always going to scan the index. Okay? I always want them to change it index scan if it's truly scanning, or index match if it's actually some matching columns that actually going to, or index probe, you know, whatever word they want to use there.
If you do the predicate analysis there, it tells you whether it's a predicate is a screening or predicate is a matching or predicate is a stage 1.
Yes, and that's actually coming up here. Yeah, matching, screening on the index.
That's basically, if you do the predicate analysis, then it tells you whether that predicate is scanning or matching or screening.
That's right. So what he's saying, when we click on this node right here, this IX scan node, this is going to show us the predicates that are being applied at the index. And as we go look at this, we'll have some screens coming up here. This shows us exactly what's going on in there. Is it a matching predicate? Is it a screening predicate? And then the other ones, you know, stage 1, stage 2, we start seeing those up here in this fetch box. Yeah, that's, thank you for that, but it's coming up. So here's some, in ZOS, we have something called stage 1, stage 2. In LUW, you don't have stage 1 and stage 2. You have like sargeable and you have residual predicates, which really the bad ones are the residual predicates. Those are the ones that happen very last after all kinds of like joining and stuff takes place. On the ZOS side, there's a lot of what we call stage 2 predicates. Stage 1 and stage 2 predicates have been around on the ZOS side for 35 years, been there for like ever. But we never had any explain tools that showed us, you know, are any of my predicates stage 1 or stage 2? Stage 1 predicates are our efficient predicates. Stage 2 predicates are our more costly predicates. Stage 1 predicates get applied first. All those rows in get passed to the stage 2 and say, hey, I got these other stage 2 predicates now, will you put your logic against these rows? Okay? So they're more expensive. We want to try to stay away from them. Luckily, in version 9, version 10, version 11, they've taken away a lot of the stage 2 predicates and made them stage 1 predicates. And a lot of it has to do with the query rewrite. The optimizer's rewriting a lot of the queries. They rewrite a lot of our queries, our predicates on the LUW side. They rewrite a lot of our queries on the ZOS side. They're taking a lot of the poorly coded predicates that developers code, and the optimizer is actually rewriting them in a more efficient way. And this is kind of what we're getting back to again. There's a lot of ways that we can write logic in SQL, and some of it is just not very efficient to the optimizer. So the optimizer is starting to get a little bit better, a little bit better, a little bit better on the query rewrites. So, you know, here's a good one right here, where a value is not between column 1 and column 2. Not all of these are being rewritten. Some of them are. But we can still rewrite a lot of them ourselves. This is one that's not being rewritten. A value is not between those two columns. A little bit different between. Usually we have a column is between a couple of values. This is where a value is between or not between a couple of columns. Well, if it's not between those two columns, that value's got to be less than that, or it's got to be greater than that. And we can rewrite it that way. And when you rewrite it that way, they become what's called stage 1 predicates. They become what's called indexable predicates. Because some of the ways that we write our predicates in the SQL language also get put into a non-indexable category. And what does that mean? That means even if there's an index on that column that I have in my where logic, the optimizer is going to go, hey, I got an index on that. Oh, but the way you wrote your where logic, I'm not going to use that index. It's going to go start looking for other indexes. So the importance of how we code our predicates and how we code our queries is of extreme importance. And developers sometimes don't know this. They just know they're getting the data right, they got the logic right in their queries, and if it didn't come back very fast, it's not their problem. It must be a database or a network or some other kind of problem. But a lot of it is the language is the problem. It's not good in some of these relational database systems like DB2. So there's some other, examples there. In LUW, we get what's called sargeable predicates. No stage 1, no stage 2, they show up as sargeable. So we're going to see when we get into using indexes get put in some different categories in LUW, start, stop keys at the index, sargeable at the index, and sargeable down here, or a residual, if it happens to be a residual kind of predicate that happens to take place after all the joining. If you do all this join, all this I/O between a couple of tables, and then you got a predicate at the very end kind of gets applied, that's not very good. Okay, let's see if we can filter before we join. Let's see if we can rewrite that some different way. So here's an LUW screen here, and then you'll see the predicate type. It says sargeable. Okay, this one right here, by the way, higher date minus 7 days is a little bit more efficient on the LUW side than the Z side. This higher date minus 7 days on the Z side gets knocked down to what's called a stage 2 predicate. Stage 2 predicates are automatically put in the category of non-indexable. If I have an index on higher date, and I have where higher date minus 7 days is greater than some date or whatever the logic is, DB2 is going to go, I'm not going to use that index because you have some mathematics on that column. So another standard is we should not put any kind of mathematics on our columns. You can put it on the other side of the operator. I mean, higher date minus 7 days greater than some value is the same thing as higher date is greater than that value plus 7 days. You put the logic on the other side of the operator, and that's perfectly fine. Just don't put it directly against the column in your where logic. And same thing with functions. Although a lot of the more common functions, like where year of higher date equals 2018, that's being rewritten by the optimizer, which is good. That's a very common, But so many versions ago, that was a stage 2, non-indexable, but non-indexable on the LUW side too, non-indexable predicate, where the date of a timestamp, equals something. Some of those more common ones like that are being covered by the optimizer now. But when you get into all the other functions, where the R-trim of last name equals Andrews, stage 2, non-indexable, so we still have to kind of watch a lot of the other functions. The more common ones are now being rewritten. Because if I say where the year of hire date equals 2018, this is something I go back on projects on, like, no, we don't use that year function. You say where hire date is between 2018-01-01 and 2018-12-31. And that's exactly what the optimizer does now for us. Okay, so filter factors. When we break this down in here, we see what's called filter factors. This is the percentage of rows that DB2 thinks each predicate is going to affect. Last name equals Smith thinks it's going to be 0.0024% of the data. So you take 0.0024 times 51,834 rows in the table. That's how many rows the optimizer thinks, if I just run that predicate all by itself, is going to get back. Is that reality? No. It's a guesstimate, and it's guessing it based on the statistics that it knows. So whenever you have some where logic here, the optimizer is going to go, oh, you have a where clause on last name. Let me go see what I know about last name. What's the cardinality of last name? Oh, 947. You're looking for one value. Do I know anything about Smith, or do I know anything about any other last names? If it says no, it's going to take 1 divided by 947. And that's the percentage of rows that it thinks it's going to. And it'll do the same thing for host variables. So it's the most common type of filter factor, because we use host variables like often. If I say where last name equals host variable, okay, it doesn't know what the value is, and it's got to come up with some access path not knowing what the value is until a query is executed. So it's going to take 1 divided by the cardinality. Oftentimes that's perfectly fine. But if there are some outliers, that's when we have to have some special statistics and we have to change our code. First name has 260 values. 1 divided by 260 equals 0.0038. So it's assuming that every first name is 1/260th of the data. They're all evenly distributed. Okay? Well, they're not evenly distributed. They could be pretty close, and it might be okay. So when we come in, this is what I particularly like about this. We can click on the table, and we can get all kinds of information on the table. I can go look at all the properties of this table. Like, How many pages of data are all those rows on? What's the average row length? You know, all kinds of physical kind of properties. I can go look at all the columns. You know, what are the columns? What are their definitions? What's the cardinality of every column? How many different last names? How many different first names? How many different department numbers are there in the table? And you just go on and on and on and on. So I can do a select asterisk and click on this, come in here, and in 10 minutes just start working my way down to, and I know the data pretty well. Okay, this is to me, this is great for developers. It's quick and it's easy for them because they don't know their data very well. At least I find in my experience. And a big part of that is, in their defense, they don't really have a tool that really shows it to them very well. You know, mainframe catalog manager tools on ZOS. Very frustrating. Okay, so table scan. If you get a table scan, we're going to see a table scan node. Okay, pretty straightforward, either on either platform. You know, we don't want table scans typically. I mean, out of the probably thousands of queries I've written over the years that are running in production, probably less than 1% of them did I ever want. I truly want a table scan, and that was only because I was going to process most of the data in the table anyway. So for developers, like, look. Take that query, cut, paste, explain, and let's just look for a few obvious things. Table scan, let's look for that right away. We don't want scans going on. And we get the estimated number of rows that it thinks by scanning that table is going to come out based on our where logic. So why would an optimizer choose a table scan? Okay, well, there's a number of reasons here. We got a couple of pages. You know, maybe I have my predicates coded in a non-indexable way. Maybe I got functions, mathematics on it, and the optimizer said, well, I got some index I could possibly use, but the way you coded your where logic, I'm not going to use the indexes. Maybe in my where clause, there's no index that match what's in my where clause. Most of the time, DB2 is going to choose an index based on our where logic. Not always. Sometimes I can have an order by and it may choose, or a group by and it may choose an index based on what I'm grouping or ordering. It could choose that index. But most of the time it's based on my where logic. So if I have where salary is equal and bonus equals, if I don't have an index on salary and bonus, it has no choice but to do a table scan. Maybe the table's small. Okay? Small enough, you know, I'll just scan the table. Doesn't mean we shouldn't have indexes on it. We still need indexes on small tables, but it might just say, I can just scan that pretty quick and easy. Maybe the statistics say the table is small. This is pretty common in test environments. Okay? Maybe I have 128 million rows in a table, but nobody's run stats for the last year, and it still says I have 28,000 rows in there. DB2 is going to base all of its optimization on what it sees in the statistics in the tables. So we as developers need to make sure we see some discrepancies like this and get with the DBA and say, hey, can you run stats on these test tables because they're way out of whack. Okay? They're very old statistics. If the predicate's such that DB2 thinks that a query is going to retrieve a large enough amount of data. Sometimes 30, 40, 50% of the data in the table, if it thinks that's going to meet our where criteria, it says, I'm just going to scan the table.
You get this if you code a lot of ors.
What's that?
You'll get this if you code a lot of ors.
Yes. I think that might come up here, actually. So, number 9. Very good. Sometimes there's just too many conditions in the logic. Or this, or that, or this, or this, and that, or that, and this, and just too many conditions. There's not one or just a couple of indexes that can fit. Says, I just got to scan the table and start looking at every row in the table. Okay? This is quite typical with many predicates that are word together. Yeah. Sometimes if the files are physically out of shape, we don't see that too often in production environment. DBAs are pretty good about keeping up on. This is a good one right here. This is one in our table that's got 51,000 rows. If you look at the properties of that table, you're going to see that the table is based on 4K pages. So 4,000 byte page has so many rows to it. If we look at the properties of that table, it's got 947 pages house the 51,000 rows of data. Okay? The data is in employee number order. If I come in and say where department number is in, and I give it a few different department numbers, and I actually run my query, and maybe I get like 800 rows back, okay? But I go and I do an explain, and it says it's doing a table scan. Like, man, why would it do a table scan? I'm only getting 800 rows back. I mean, typically the indexes would get used because we're not getting that large amount of data. Well, the 800 rows that we get back, where are they in that physical file? They could be on 800 different pages because the data is not clustered by department number. So it's like, wow, these things are so scattered, there's only 947. I think you're going to get about 800 rows back. I'm just going to scan the table. Because it'd be faster to scan than to individually keep hitting these pages and bringing them from the physical file up into the buffer pool memory area. So that can be very misleading sometimes. You know, like, wow, why is it doing a scan? I'm only getting so many rows back. You know, and that we can get into the tool and figure that out here versus just seeing a regular scan in an explain output. Go a little bit deeper. Okay, what we get out of the main table on ZOS and some of the main tables on the Z side is it'll have like access type of I and say some matching columns. Okay, we want matching columns greater than 0. That's going to actually probe the index, split that root page and go one way, left or right, and find the entries or not find the entries that we're looking for very quickly. If I see access type of I and matching columns is 0, that means it's scanning the index. But the node looks the same in the output. Okay? In the explain, if we get explains any other kind of way, we see matching columns, you know, here in this table and other tables on the LUW side. If we come into Data Studio, we click on where the predicates are being applied to the index. Remember, predicates, where predicates are going to be applied here, and the other ones are going to be applied here. So we need to click on this, and we need to go see what some of the information is. You know, do we have any matching columns? You know, do we see anything that says matching over here? If we see matching over here on the ZOS side, that's good. That means it's probing, it's slicing that index. We don't see the word matching on LUW. We see what's called start-stop keys. I think I have some examples of that coming up here. So another thing that we need to look at is what's called screening predicates at the index level. So here we have a query that's going after the first and the third column of the composite index. There's nothing on the second column. So, you know, go back and think about how that index is ordered. It's got last name, first name, middle initial. And it's in that order in the physical file. So when it probes that index and it hits the last name equal Goldsmith, it has to stop. Why? Because it has to go through every single Goldsmith to see who has the middle initial of R. Because Goldsmith could have a whole bunch of them there with different first names. And that's the start-stop keys that you see, you know, a little bit kind of better definition, I think, on the LUW side. So this one right here is called a screening predicate. The matching columns is only one, which can be misleading to a lot of people. Like, well, I got two of the predicates of the index coded. Yeah, but you skipped the second one. So it can only slice through the index and probe it based on the last name, the one column, and it has to stop at that point in the physical file and then start checking through all the first names. In the Data Studio tool, when you click on this, we will see the categories that they're put into. If there's any screening, we're going to see a screening folder. Matching, we're going to be put into a matching folder. If you go forward here on the LUW side, we click on this, and we're going to see start-stop keys here. Okay? Start-stop key would be, you know, start at Goldsmith, and the stop is going to be at the end of the Goldsmiths. If we don't see anything over here that says a start and a stop key, as you click on these predicates and come down, if we don't, then it's scanning the index. So on the Z side, we want to see matching columns. On the LUW side, we want to see start-stop predicates as we click on this here. Or it's going to be doing what's called an index scan. The screening in the LUW side doesn't get put into a screening folder like we see on the Z side, but we see them as what's called sargeable predicates at the index level. So they're put into a sargeable category, which means they're screening. Okay? So sargeable at the index level in LUW means screening. Screening at the index level. Wow, 10 minutes left. This went fast. And non-matching, of course, the index scan. Okay, I'm going to roll through here a little bit quicker. I got some other things I want to make sure I hit on. So here's one here. When we click on this, we go over to the LUW side. There's no, as you click on these predicates then, Because when you click on one of these nodes, it's going to show you the predicates that are being applied. When you click on those, if you don't see it, if all you see is sargeable predicates, there's no start-stop key. It's going to scan the index. If you get an index only, we don't even see the data file. We just see the index file. Okay, that could be a really good thing. If we get another physical file out of the way, that's less I/O that can be done. So this is where we get to what I call kind of SQL programming 101. Only select the columns that you need. And there's a lot of queries that run in production that have extra columns in it that they're not even using in the code. Okay? Why is that a problem? Well, sometimes it could be a huge problem. Well, what if we have like 10,000 last names that begin with J-O? And what if they had in here last name, first name, middle initial, salary, bonus? Where does salary and bonus live? They live over here in the data file. This, being a non-clustered index, 10,000 rows could be on 10,000 different pages. It could be getting 10,000 pages out of the physical file for what reason? To get salary and bonus, because they don't live on the index file. It could be doing 10,000 IOs to that other file over here to bring columns back that they don't even use in the code. So it sounds real simple, and a lot of times in walkthroughs, people go, really? You're going to make me take that one column out of there? I'll go, yeah. I mean, why do you want it to begin with? Does your program need it? No. Then why then get it out? We don't need it. Get it out of here. It can cause some major I/O sometimes. Okay, here's just a way to show some of the joins that go on. The nested loop join. They have a hash join on the. I'm not sure I have a slide of that hash join on the LUW side that we do not have on the Z side. And it'll say hashing in there. Nested loop. Merge scan, both platforms have a merge scan join. Merge scans don't always do sorts of both files, but it only goes through each file like one time. Oftentimes there is a sort that's done because what we're joining on between the two tables is often a column that both tables do not have an index on. Like maybe the start date here equals the start date here, and this one doesn't have an index on start date. So DB2 is going to say, okay, I'm going to get these two in start date order, and then I'm going to start doing my comparisons. So merge scan joins, I always look, if you have some tables that don't have indexes or a missing index, you're going to see merge scan join come often. And also if you're not doing much filtering, if DB2 thinks of the two tables, you're going to be getting a whole lot of data back. This can be a faster way. Hybrid join on the mainframe. This kind of first goes into a quick little semi-join here in this output. And the semi-join is let's quickly go probe that index on the other table, and let's right away get some hits. Because I think if I go from here to here, I'm going to eliminate a whole lot of rows. Now, why would the optimizer think that? Because maybe if I'm saying we're employee number here equals employee number here, and the cardinality in the statistics say I have 51,834 employee numbers here, but over here I only have 8,000 different employee numbers. As I join those, a whole lot of them are going to get dropped out, right? So it does this quick little index join, and it kind of works its way through the rest of the process there. But that's the way that the hybrid join looks kind of different here, but that's what's going on down here real quick for some elimination.
What's more efficient, merge join, hash join, or index join?
Yeah, it does depend. There are specific reasons, why that we can't get into each of them here right now. A nested loop join, for example, if both tables are in the same clustered order, department number here equals department number here, then you're going to see nested loop join most often. When we're joining on and we have unclustered, they're not clustered in that way, then it really depends on how much filtering is being done on the tables and the indexes. And merge scan, like I said, will be chosen without indexes. Global temp tables, good example of that. Nested table expressions, common table expressions get built, no indexes. You'll see merge scans often. Sorts, all kinds of ways we can get sorts. All I do is tell developers, if you don't need a sort, don't do it. So there's a lot of reasons that a sort could be chosen. It doesn't mean a sort is going to happen if I have some of those in my query, but they could. And the only way we really know is to do and explain. and we see a sort node. And then another thing is sorts are very efficient in DB2. So if I see a couple of sorts, that may not be a runtime problem. How many rows are going into the sort? 5 or 10,000, 128 million? It's going to make a difference on the expensiveness of the sort. But sorts are pretty efficient in DB2. So there's another sort node there. Okay, we get into the optimizer. The optimizer does a lot of query rewrites for us. There's something that's gone on for quite a while. It's called transitive closure in SQL programming. It has to do with joins, comparing one column to another column. So a couple of examples here. If you compare a column even to another column in a row, and if one column equals some value, then that means the other column's got to equal that value. And we'll see this come out, and this will be added to our query before it actually goes through optimization. And why does it do that? Because now it's going to go, oh, now I can go look and see if there's an index on administrative department. Now I can go look and see if there's an index on department number. If it stays there, okay, it's only going to see if there's an index on administrative department. If there is, it's going to use it. But that might not be the best index. So this can be kind of tricky, because you can look at this query like this and look at it and explain and see that it chose an index on department number. And you go, well, I don't even have any where clause on the department number that we see in the query, but we do from the optimizer. You can see these rewrites in the query tool. And there's a lot of different kind of rewrites that go on, both in LUW and the ZOS side. In predicates, transitive closure will happen for every predicate type except a like. If you come in and say we're D.department number like A%, it does not add E.department like A%. So with the like predicates, we need to do the transitive closure as developers. All the other predicates, and this is one that came out in version 10. Some of these have been added over the last couple of versions, but the like predicate's still not there. Okay, let's go forward here. When you do a scan, or when you do an explain on the LUW side, this is great, because up here in the tool, you can come up here and you can select, let's take a look at the SQL. And when the SQL window pops up, you can see an original, or you can see what's called an optimized. It's a little bit more convoluted on the ZOS side. We have to go into what's called tune a query, as opposed to just the explain, to see what, and it's called transformed over there, but the same idea. Because sometimes I want to see, what did the optimizer do to my query? Did it do anything different? Because I may be looking at explain and not quite understanding what's going on there. But when I see the rewrite, that helps. So this button right here takes us down the path of, on the mainframe side, to see what's rewritten. And it may look the same. The original and the transform may look exactly the same. It didn't do anything different. So we come in here, there's a couple of pages on how to do that here. Okay, we get some statistics advisory information out of this. I want to go forward to a couple other screens here. I only got a couple minutes. A couple of pages on just, again, why does it choose one index over another? I can come in here and say, well, it chose that index because it thinks it's getting much less data out of that particular column and that index than the other one. Okay, kind of tells me the story of why it chose a certain index, why it chose a certain order of tables. All right, I'm going to go forward here. I only got a couple minutes. This went fast. Frequency statistics. So statistics help. When we have frequency values, what values have a percentage of rows in the data. But we can have all the greatest statistics on data distribution that DBAs have run, but if I don't hard code, we cannot take advantage of them. If I come in and say where department number equals host variable, I can have all the greatest statistics on distributions and values and stuff. It says, but I don't know what value you're going after. So I can't really do anything for you. So it's going to take 1 divided by the cardinality of that column is going to be the filter factor. Okay, I'm going to kind of go forward here. Some additional statistics to show. Here was one on the commission column. I told you like 90-some% has 0. And then, we come in and we see a whole different, but we have to hard code. That's the key. And if I'm going after any other value, I need to add and e.commission does not equal 0. Because it's going to say, well, what do I know about that? Well, 0 is 90%. You're going after, you're saying it's not equal to that, it's equal to something else, so it's got to be very low filter factor. Not much data is coming back. And last couple pages here, there's something that came up in the ZOS side called a sparse index that we see now. It's very similar to kind of hash joining on the LUW side. And this is great when we get into some joining of tables, or I have to scan one of the tables, or if I have in logic that's going to get a whole lot of rows back on some in logic, or if I have a nested table expression. Let me go forward here. If I have there's a common table expression here, we see that sometimes these expressions are going to get materialized, but prior to version 11, when they get materialized, they're put into a physical file, but there's no indexes on there. And sometimes I join that to some other tables. Well, if I'm joining again with a table and this has no indexes on it, we would see merge scan most all the time. So what the optimizer is doing now is just materializing that information and is putting that into what's called a sparse index in memory. Okay? And it's hashing those values, and then it goes into a nested loop join here. So it's kind of building an index for us. This is great. We see this a lot. If I have where some column is in, and I give it a list of values, it'll take that list of values sometimes and put it into a work file with a sparse index. So we see this a lot more coming out of version 11. It's a good thing. Okay, so that's what that node is all about. Okay. That's it? Any questions? Anybody? Yes.
So I do a lot of tuning with Data Studio. One of the things I've noticed is that it doesn't really seem to have enough smarts to recommend and index on expression. Have you run into that?
Yes. Yes, because we don't really get any index recommendations out of the no charge tool. Okay, you get statistics recommendations. If you upgrade that, then it will take advantage of that virtual index that you can do, and it'll actually do some things behind the scenes and then say, oh, this could be good.
Well, I've got the query tuner.
Okay.
Query workload tuner, but it still does not recommend an index on expression.
Oh, okay.
Yeah. And the other thing I've noticed is that sometimes, it'll say a query is like really expensive, but I just want to see what it actually does. I run it, it's like that.
Yes. The costing is very much of a guesstimate.
Yeah.
We get costing numbers, all kinds on LUW. We get different costing numbers on ZOS, and I've had the same experience. So I usually tell people, don't do rewrites and base everything on the costing numbers that come out. You have to go test. But if I have an environment that really, because a lot of companies, they have environments where they copy production statistics to a test environment. There's no data there, but all the tables have production statistics. If that's all I have to go on and costing numbers come down, I say that's when we're going to use it. Other than that, we got to test it with some data. Yeah. Anybody else? Yeah.
Can we do all of this with Data Server Manager, or do we?
You can. Yeah, so DSM is kind of the new and improved, and it actually goes deeper than this. This is not going away. Data Server Manager will do the same thing. The visual explains, the clicking on the nodes, getting information. Yes, absolutely. But the one reason that you really need to keep this is for SQL PL stored procedures. Because DSM does not have the window, the editor window for SQL PL. It doesn't have the deployment, all that. It's not even a part of it. It's just for optimization. Yes.
Yeah, it's also for, if you're using it on the mainframe, it's really more LUW centric, because on the mainframe, we work with some different things, and there's a lot of tables you have to implement. You can't separate just the visual explain, because that's all we wanted. It's really a full-blown tool,
The DSM?
the DSM.
Okay.
I mean, it does seem like it's going to be easier to manage if you can get it going, but there are hundreds and hundreds of tables that you don't know before.
Yeah. It's easier to install, I know that, than
Right,
this.
that's
But
the idea we had, is we have to install all these multiple versions of it at everybody's desktop. But the problem is that we have top secret, so it didn't support like a pound sign for a user ID.
yeah.
And you have to have a persistent ID that connects to the repository to verify you as being a user. And so there's a lot, if it's a mainframe part, you gotta be careful with that.
Yeah.
Because we heard the data studios went away, and we said, well, we better replace them.
Yeah, it's not going away. If they do any kind of like grandiose changes to a visual explain, they're going to do that in DSM, and they're not going to upgrade this. But the visual explain, the only thing I've seen change in a visual explain here recently is that sparse index that shows up now. Okay.
Thank you.
Anybody else? Okay, thanks, guys. Have a great day.